Welcome to CIVE632, Computational Hydraulics. This is the fourth week of the class, virtual class, fall 2021. And today we're going to discuss and cover various aspects of the Muskingum-Cunge method. But prior to doing that, I'm going to spend 5 minutes showing you how we did the conceptual model. And in order to do that, I am going to go over here. Let me see if I can, let me see. What are you seeing on the screen now? Is it blue?
Yes.
Yep.
Okay. This is the paper, the math paper I wrote in 1997 with Summer Hassaning was a student, and Professor Cordero Braña was a math expert who helped me, both of them helped me integrate the formulas. The formulas are very complex. And the answer for this, what we wanted to do was to do what Duke had not done, because Duke had done 3 of the 5 curves, and we decided to do all the calculations, as you can see, and we plotted the 5 curves. There's 1, 2, 3, 4, 5 curves in there. So I believe we published this paper not because it was a novel method, because it was published in 1997, and Duke been doing this for 40 years. But it was because it was comprehensive, it was complete. It had the 5 versions. 1 is linear, 3/2 is Chesi, 5/3 is Manning, 2 is Horton, and 3 is Izzard. That's the way they are called. And and number 6 is the kinematic wave. The kinematic wave is over here, and all the conceptual models that I just mentioned are over here. And you see there's quite a difference in there. And the difference is explained in my book in chapter 4. So if you want to get in there in more detail, you could go ahead to chapter 4, section 4.2 of my book that would explain the difference. Why is it that the kinematic wave is fast while the diffusion waves, these are diffusion analogs, so to speak, and they are slower in the response. And in addition to that, I am going to see, where is the share in here? New share, right. In addition to that, I'm going to share now the calculator. Can you guys see that? Right?
Yeah.
Yes.
Okay, cool. I need somebody to say right so that we know we're on the right track. I'm just going to give you an example of how these things are done. I'm going to run SI units with Izzard on the rising limb only, although this calculator can do all of them together, rising and receding. Okay, in the length, I believe I'm going to use, let me go in here on the sample input. The length is 60.01, 30, I think I can remember this. The length is 60. The slope is 0.015, that's 0.1%. The effective rainfall 30. This is just example in the calculator. Manning, because it's Izzard doesn't use Manning, so we're gonna put a 0 in there, or don't fill it up. Okay, and then we're gonna do the calculation. And this is the calculation, and these numbers are correct. The equilibrium outflow is 0.5 liters per second per meter, because this is an overland flow plane calculation, and the time to equilibrium 520 seconds. So as you can see, we have solved this problem for the 5 versions plus the kinematic wave completely. All formula, no, these 5 formulas, not the kinematic wave is not here. Okay, so that's just an example. You can try it out on your own time, and you can see how it works and so forth. So with that, then what I like to do now, let me just cut this. I'm going to cut it so that it doesn't crowd my screen in here. So now I'm going to do now, and I'm going to go in here, and today I am going to cover BO1, BO2, BO3, and BO4. Hopefully, I'll get there. So let's get started with BO1. In order to do that, I have that already, and now I'm going to screen share BO1, which is this. So now you should be getting a green screen. Is that correct?
Yes.
Okay. By the way, that green color is my flagship color of the Visual Lab. I have 2 flagship colors, 792 and E61, which I chose many years ago, 20 years ago, as the flagship colors. And they're on all my videos, by the way. This is just a small detail. Okay, so we're going to talk about the first of four papers that I'm going to cover today is one of them is titled Muskingum-Cunge Method with Variable Parameters. Okay, what's the story here? The background. The background is that the Muskingum method was developed in 1938. We know that. And that Cunge came up with an improvement in 1969. Um, but Cunge really didn't talk about an example calculation. He was talking about theory, and he did a great job, although he made some mistakes, but it was a great job. So we needed to do a calculation. In addition, I think I mentioned to you that Wallingford, Price of Wallingford in England, had already talked about the Muskingum-Cunge in 1975, but they said that it was used on a linear mode, and they said in their paper, in their report, it's actually a blue cover report, that they would like to see the nonlinear mode because obviously that was the next thing to do. So I read Price and I picked up on that idea, and I was eager at that time to do all this because I think I already told you that my first 3 years at Colorado State in the mid 70s, I discovered or learned, I guess you could discover is too strong a word. I learned about numerical diffusion. It was very not well known at that time. It was only 4 years since Cunge had introduced it. And I was fascinated by it. We were studying numerical diffusion under the Priceman scheme, not under the Cunge scheme. But once we understood that there was this thing called numerical diffusion, which was not diffusion, but of a numerical nature, I was fascinated by it. And I thought I was going to do the work that Cunge had done. And when I read the Cunge paper, that I realized Cunge had done it already. So I figured all I can do at this point is follow Cunge and propagate his ideas. And so that I did. And the first thing I did was write this paper, Muskingum-Cunge with variable parameters. I put my co-author here, Professor Yevevich, because he had helped me out through the years. And he was a real nice gentleman, and I learned a lot from him. He's Professor Yevevich, Wujitsa Yevevich from Colorado State. So I'm going to go, as I always do, read with you my own paper. I will touch upon the salient points, which I think should be discussed or covered at this time. If there's any minor issues out there, then you can study them on your own, or you can, as I said earlier, I repeat, you can bring them up at any time later on with me. I'm here to cover these subjects. So the Muskingum method and its improved Muskingum-Cunge version are well established. In flood routing, it's flood routing. The Muskingum method is based on the assumption of a linear relationship. So this relationship, one, is McCarthy's. This is what McCarthy. Unbeknownst to McCarthy, this is really a way of saying kinematic wave, but he didn't know that. McCarthy did not know about the kinematic wave because the kinematic wave was brought upon in 1954 and McCarthy was writing this in 1938. It's very important to look at the history and the timing of these things. Okay, so we report the Muskingum-Cunge version, okay? It is shown that the way of calculating the parameters has a definite bearing on the overall accuracy of the method. We need to give credit here to Duke, who was using the Thomas method, which we will use in our number 3 homework, or rather on our number 3 problem, and in the next couple of weeks. And Duke was saying that the peak flow, the amount of the peak flow or the value of the peak flow depended on the reference flow that was used to do the parameters. He said that. I do not recall, I don't think he advanced the idea of varying the reference flow. But since Price had already said it, and Duke had done the thing that the constant parameter, I decided I was going to pursue that. So I did. I wrote this paper and consulted with Professor Yevevich, and then we published it in the year, I believe it was in the year 1978. And this is the original version of it, Muskingum-Cunge method with variable parameters. You can see that, right? Okay. Are you seeing the green page? Yes, no? Okay, we report. Okay. It is shown that the way of calculating the parameters has a definite bearing on the overall accuracy. As shown by Duke, the assumption of constant parameters makes the solution dependent on the reference value. Okay, what is the reference value? You need a value or values to calculate the parameters. So if you choose one value, you're gonna get an answer. If you do what we do here, which is let the value of the parameter be vary throughout the flow, then you get a different answer. And which one is the answer? Well, the true answer is the variable parameter because the world is quasi-linear. I already explained that the other time. But the linear method is an approximation. It's a good approximation. Besides, we need to keep in mind that we don't know everything, and these calculations that we're doing in here are referential in some sense. Referential. They're typically used for design, meaning design is always referential. I'm always choosing a frequency and I'm going to design for the 100-year frequency or 1,000-year frequency. And I hope that that happens because there is no certainty that the 100-year frequency calculated will be the effective 100-year frequency, particularly now that we have global warming upon us. The entire record could be at risk of obsolescence. I've said that, and people have said that. So what we are doing here is a rough calculation. It's a calculation that could be considered at best rough. Okay, so there's no perfection. So that is why the linear method is still defensible, because we say, well, the difference is small, and therefore we can still use the linear method. And it is my opinion that the linear method is used in practice, and the nonlinear method is used in research. That's about as far as I'm going to have say. Several years ago, a group here from San Diego that are doing this kind of stuff contacted me about the nonlinear method, and they said they were going to pursue it. But these people are researchers; they're not practitioners. I happen to know that. You know, it's a research lab here in town that we're doing this. So as you can see, I'm going to say that the nonlinear method is fine, it's good, it's better, but it has its nuances. It's not perfect, but it is for the research. And there is always research out there. There's researchers. I mean, you know, 5%, 1 to 5% of the people that are practicing are researchers. They are trying to advance knowledge in the field, right? So the Muskingum method we already know. And if you are not familiar with it at this point, then review it. The equations are all in there. It is very clear. Okay. The little bit of magic is this plot in here, which is supposed to be the space-time discretization. If you have never done this, it's going to take you some time to figure it out. I know that for a fact. I've taught this for many years. Students run into a stumbling block when they look at this. They say, what's J, what's N? Let me think about this, right? So if you haven't figured it out yet, you got to figure it out on your own. But we got a space, and we discretize the space so that we can pick up numbers out of the space. So these are the formulas of McCarthy, the original Muskingum. McCarthy identified K and X, K for the transfer or the translation, and X for the attenuation. And he gave some ranges and so forth. He basically said that the K could be found from the set on celerity, but he gave no indication as to how to calculate X. And for a long time, from the late 40s to late 70s, the X was considered a big mystery in hydraulics, or I'm sorry, in hydrology. The Lindsley book, which was used in the United States and around the world throughout the 50s, 60s, and 70s, basically said that we didn't know how to calculate X. The book said, try 0.2 and run with it if it works for you. That's more or less the way he put it in his book, Lindsley, Hydrology, Applied Hydrology, I think it is. Okay, so we didn't know at the time about X. Then Cunge came and he confirmed that in fact the set on celerity was instrumental in calculating the K. And he also gave us this fancy little formula, which I already told you last time how we derived it, or how it was derived, which was not written as like as Cunge, but it's written as Price. Price did it this way. You don't have access to the Price book, and I don't think you could have access unless you went to the library and checked it out. I think the San Diego State Library has the Price book. It's called Flood Studies, written by an English agency. I think it's quoted somewhere, but it's not necessary because I've given you everything that you need. So what I want you to do is to try to get from Cunge to here, because this is what, in other words, I saw Cunge and I saw Price, and they were different. I said, well, I mean, I got to check to make sure that they are the same. And in fact, they are the same. So I want you to verify that, in fact, the Cunge, the original Cunge formula in his paper is the same as the one that Price uses. Okay, so that's it. Then Professor Ponce came up with this. I converted because I knew the Courant number. Okay, where is this thing? I think not in here, but somewhere else I've written. Okay, now here it is. I developed C and D. I knew the Courant number, but because that's basic. Remember, I talked to you about Courant, Friedrichs, and Louis. But the cell Reynolds number was not known. But then I realized that the Courant number was a ratio of celerities. Is the physical celerity over the grid celerity, the delta X over delta T. And I figured also by looking at D, you could see that that is in fact the ratio of diffusivities, because Q's over S of O is diffusivity. It's Hayami diffusivity. Is half of the Hayami diffusivity, or the total, twice the Hayami diffusivity. And CDX is an expression of what Cunge found in his paper that I explained to you last time, in the last period. So D is a ratio of diffusivities. So the question was what to call it. And every time you are at a crossroads, you got to call something, you got to be careful. Just because, okay? So I have read the book by Roach. My memory's messed up. Roach, Roache. He wrote in 1972 a book called Computational Fluid Dynamics, which is an excellent book. It's at a higher level than hydraulics. You know, fluid dynamics is always at a higher level than hydraulics. And he was talking about a Reynolds number, a cell Reynolds number. But he defined it as a reciprocal of this. In other words, he wasn't defining like I do. If he had done it, he would have said CDX over Q's over S of O. I didn't like that because if the Courant number was a ratio of physical to numerical diffusivity, the cell Reynolds number had to be a ratio. I'm sorry, if the Courant number was a ratio of physical to numerical celerity, the cell Reynolds number had to be a ratio also of diffusivities, where the physical diffusivity on top in the numerator. So we did that. We also found out that in the literature of contaminant hydrology and hydraulics, what Roach had called cell Reynolds number was called a Peclet number, Peclet, with an accent. It's a French. Apparently, Peclet was a French gentleman. They used those accents, reversed accents from Spanish, you know, because English doesn't use accents at all. But the French use a lot of accents. And I think they call it accent. I don't know French, so I'm not going to get in there. But the point is that Roach's cell Reynolds number is effectively the Peclet number, if you consider it across different fields. So we are, the Peclet number is not something that, I'm sorry, what am I going to say is that it's not something new, it's been around. I have not researched because I'm not into contaminant hydraulics. I shouldn't say that because all this stuff is really the same. But the point is that's a Peclet number. So if you hear the Peclet number, that is it. Says the Roach cell Reynolds number. But I reversed it because I didn't think I was going to do something wrong just because other people had done it wrong. So I was trying to fix it. So I did this D in here, physical and numerical significance. C is the ratio of celerities, D is the ratio of diffusivities, and I let it go. I put it in this paper. The celerity is the 7, 11, formula 11. And Q, lowercase q, is the discharge per unit of width, okay? And now we say we can calculate the variable parameter. Imagine a grid where you have a bunch of reaches and a bunch of time steps. So this grid is not just like this. This is only one, but it has a whole bunch on the right side and a whole bunch on top. You could have 10 by 1,000. You know, it's a mesh. It's really a mesh. Grid or mesh is both of them are used in numerical hydraulics. Okay, so we were going to do this in three ways. We will use 2 points. In other words, we could use the Q and the C and the Q in the average of 2 points that were known, or you can use the average of 3 points, 2 of them known at base level or at n level, and one n plus 1 because we already knew the n plus 1 on the flow coming in, or by iteration using a 4-point average. But the 4-point average could not be done initially because you don't have the 4th point. You're calculating the 4th point. So the way to do this, we figured out that you could use the value, the 3-point value is an initial start of the iteration. And then the iteration would converge readily within 2 or 3 iterations. And we felt that it was going to be better. And since we have a computer that's very capable, it doesn't really matter. The speed is really amazing, particularly now. It was not 50 years ago. 50 years ago, we had to be careful about what we were putting on the computer because it could take too long. Not anymore. I don't have that problem anymore. Okay, let's move on in here. Now we're going to run the example. I figured that since Duke had talked about the Thomas method, and the Thomas method was well known, I decided to kind of follow Duke, and I was going to use the Thomas method. So you need to study this Thomas method in detail. Not the article, I referenced the article in there, but you can go to the library and get it if you want to, but you'll be wasting time. I already gave you all the tools, okay? The problem consists of tracking the travel and subsidence of a flat wave of sinusoidal shape in a unit width channel with a steady state rating curve. So I believe the slope, I don't remember right now, but the slope is 1 in 1 foot per mile, something like this, which gives you a slope, and then the slope you can calculate the alpha. So in other words, this 0.688 has been calculated by putting in there the slope. You can review this in my papers, and it's there. You'll see it. I'm sure you'll see it. And the d to the 5/3 is because this is a Manning formulation that Thomas was using. The inflow hydrograph, this is the Thomas problem. It starts at 50 and it goes to 200. That is why you have in here 125 minus 75, because when the time is 0, the cosine of 0 is 1. So it's 125 minus 75 is 50. So it starts at 50 and it goes between 0 and 96. After 96, it's always 50. Okay, so that is the hydrograph. It's a sinusoidal hydrograph. It's right there, right here. This hydrograph labeled A. It starts at 50, it goes to 200, it comes down to 50 at 96 hours. And this is a good hydrograph because you can play around with 48, with 24, in 192, and compare the diffusivities, because the amounts of diffusion, because they're going to be different. They're going to vary with the length of the hydrograph, because the bigger the hydrograph, the more kinematic it is, and the less diffusion it would have. Right? We know that. So it's a good problem, and that's why I'm giving it to you so that you can play with it. I mean, not play, you work with it. Okay. Interestingly, though, the last 5 years, I had a very smart student, one of our students here, and I charged her, we're doing a calculator of this whole thing, of all the Thomas problem, and she did it. It took her a while, but she did it. So we actually now, and I'll show that later, have a calculator who will calculate the Thomas problem. So if you're uncertain as to the results that you're getting, check with my calculator, and your calculator will tell you. As a matter of fact, we already know the answer for this problem. It's 176.5, something on that order, for the given parameters that we're looking for. So if your calculation doesn't show 176.5, you're doing something wrong, okay, in your Excel sheet. Okay, so I'm not going to spend too much time in it, only to tell you that we did several calculations in here, and they're all plotted in here. We did B 500 miles, Muskingum-Cunge with reference flow 200. C, I'm going to have to speed up in here. 500 miles because at this rate we're not getting anywhere. 125 and 50. Then E is a variable parameter Muskingum-Cunge for 2 points, 3 points, 4 points, okay? And this is at 500 and 200. And I is somehow I pulled up the Thomas, but it doesn't really matter, the Thomas. But if you can see in here, B, C, and D, they're in here. B, no, it's B, yeah, B, C, and D. So B is over here, C is over here, and D is over here. So you can see D is very slow. Slow, it's on the right, it's slow. So B, C, and D. So if you chose B, you'd be calculating a fast hydrograph. If you chose C, you'd be calculating an intermediate because it's in the range. 125 is in the middle, average middle. And if you use the base flow, you'd be very slow. It would not be the right answer. So the best answer is to use an average method and to get closer to the real answer. The real answer is this one. The real answer is okay, now we have E, F, and G. G is the real answer because it's a 4-point, right? So G is the real answer, but F and G are very close. Because you can see F and G are, as a matter of fact, F and G are almost the same. This is F and this is G in the same curve. So this is the real answer. And as you can see, it steepens up. That's the way it should be. Nonlinearity tells you that the flood should steepen up as long as it is in the channel. If it's not in the channel, let me write this down here. If it's not in the channel, it will not steepen. It will flatten. So this is an interesting question as to what exactly is it that we're doing? Is the flood inside the channel or outside of the channel? And the answer is, well, as a matter of fact, the flow is going to start inside the channel, but by the time it gets to the peak flow, it's going to be outside of the channel. So at this point, it gets really complex. And that's why you're getting paid the big bucks to do this. Use the HECRAS and HMS. At any rate, when the flow goes over bank, it gets complex because the cross-section change. I can remember when I was in a story, you know, they say Professor Ponce has good stories. When I was in the Upper Paraguay, I was going to the field with my supervisor, and I said, his name was Hugo. I said, Hugo, I'd like to see how the flood waves steepen, because I had just come from calculating the steepening. So I wanted to see the steepening in the Paraguay. And he says, he looks at me, kind of smiles, and he says, floods don't steepen in the Paraguay. And at that point, I realized that I may have said something wrong, but I certainly was not about to argue with the guy. He had worked 20 years in the Pantanal, and that was my first day or second day in the Pantanal. So I wasn't going to argue with a guy that has experience. So I came back, and after a few years, I found out the answer. I found it, as a matter of fact, 4 years later. The floods steepen when they're in bank, but they dampen, or the negative steepening, as you could say, when they're out of bank. And since the Paraguay goes out of bank all the time, every year it goes out of bank, it was never going to steepen, right? That doesn't mean to say the floods don't steepen. In Colorado, in the year 1976, 30th July 1976, they had the Colorado Big Thompson flood. That steepened and killed 130 people. The Paraguay has yet to kill a person because it doesn't steepen, right? So anyway, so that's the story of steepening. Now you know how it works, okay? Unfortunately, though, because of all the calculations that we're doing, the variable parameter failed to conserve mass. Notice how the linear methods all conserve mass. This is really amazing in numerical hydraulics, that you can do thousands of calculations and they will conserve the mass of the hydrograph, which is a sinusoid. You know the mass of the hydrograph. You can integrate it. As a matter of fact, you know analytically the mass, the volume of a hydrograph. But you can also use Simpson's rule or trapezoidal rule. Actually, we use Simpson's rule because it's a little bit more exact to calculate, to integrate. You can do this also in Excel, by the way, to integrate and get the mass. As you can see, the mass is perfect as long as it's linear. But if it's not linear, there's a loss of mass. But we figured out that the 99% of the 4-point is a very small price to pay to get the nonlinearity. And so we said, you should do it because it's a small amount. Like I said, the 1% is nothing. I mean, after all, this is all an approximation anyway. Why is it an approximation? Because, and we say this later, we have no way of accounting for the lateral inflow. Is there lateral inflow? Of course there is lateral inflow. In the Paraguay, there's a little bit of base flow that's coming in all the time, regardless of what you do. It's a small amount, probably not to be considered as far as the flood. The flood is typically not base flow. The flood is typically coming from the surface, right? Very fast. Although the Paraguay fast is 6 months. So the Paraguay is an unusual situation. I said it at the time, it was not in my book. When was it? No, I'm sorry, I take that back. My book was 89. The Paraguay was, I was there 79. I could not have said that. But the Paraguay is not in my book. I wrote it in and I put it in, I didn't put it in there. Why didn't I put it in there? Because the Paraguay is unique. And I was writing a book for the entire world. And so I didn't do it. So that's the end of this paper, okay? And now I'm gonna go to the next paper, accuracy criteria. I read all my papers the day before or during the day because I need to put the stuff into my forefront of my mind. And you know how it is, you can forget a stuff. Even though you wrote it, you still can forget it. And I have mixed feelings about this paper. I'm going to kind of confide to you. It's got a lot of stuff in there. It looks very difficult, but it is largely unnecessary, in fact. This is not a confidence or confide to you, but also an admission that sometimes we do things that may not be perfect. What happened was that in 1980, I met with Fred Thur, a very good friend of mine. We went to school together, and he said, Miguel, we have developed the Atkin method to replace the convex method. We all knew that the convex method was bad. The convex method was a linear kinematic wave, even though Marcus that developed the convex method didn't know about the kinematic wave like McCarthy. So they were blinded as a matter of, because they didn't know the theory, neither Marcus nor McCarthy. But one could argue that the convex method of Marcus was a linear kinematic, just like Cunge argued that Muskingum was a linear kinematic. The same thing. And it will be clearer when we get there in about a couple of weeks. So so we argue that. So I said, well, I mean, you really shouldn't be doing anything other than Muskingum, I said, because Muskingum is the theory, follows the theory. There's nothing else to be done because they call it Atkin. I thought, jokingly, I thought, hey, you guys hired some Chinese or Korean guy. He said, no, Ponce. He said, Atkin for At for attenuation and Kim for kinematic. So what we do is we split the routing into two parts. We first attenuate and then we kinematically translate. I said, well, that's the wrong thing to do because it's one system. It should be together. Both of them should be done together, not separately. And he says, do you have a better way of doing it? I said, sure, we have the Muskingum-Cunge. And at that time, we ran into a political issue there. They didn't know about the Cunge part. They know about Muskingum. Everybody knows about Muskingum, but the Cunge was not known. So then he said something like this. He said, Ponce, I can give you some money if you give me a proposal, but don't use the word Cunge. I said, okay, fine, no problem. You know, you're paying, right? So I changed it to linear diffusion, which is linear diffusion. If you're going to consider parameters constant, it's linear diffusion. So this paper in here doesn't mention Cunge because it was based on the work I did for Fred Thur, for SCS, Soil Conservation Service. They gave me a contract and I spent a year working on this. So I spent a year working on this stuff. Okay, but it was at the time where we were brewing these things. I mean, we were still kind of, I guess you could say, green in terms of these, even though we had pursued it for several years. So basically what I say in here is not 100% correct. And for that reason, I'm just gonna kind of go over it quickly. And the reason why it's not 100% correct is because we were looking for accuracy. In other words, we were looking for the method, the computational method, to reproduce the diffusion wave equation, which is what Cunge had tried to do. Okay? And like I said, Cunge never showed an example. Cunge was talking about theory, but we are going to show examples in here. So, trying to do that, and so we researched the literature and we found all kinds of people that had done all kinds of things. So we figured, see, we were getting paid to do this, we were going to name them. So we named Cosis, we named Lawrenson, we get a lot of people mentioning what they were doing. Why is it? Because at the time, people were saying that the Muskingum was misbehaving under certain conditions, which is true, correct. And people were trying to figure out what conditions they could find so that the Muskingum would not misbehave. They were talking about the Muskingum, not the Muskingum-Cunge. You know they're related. They're like cousins, okay? So in here I write recent contributions on accuracy criteria. But let me say at this point, to close this issue, that there's one and only one answer for this whole problem, which I could have told you from the beginning, but I'm going to tell you at the end, is that when the Courant number is equal to 1, the third order error vanishes. And I already asked you that in the essay. It's important. When the Courant number is equal to 1, the third order error vanishes. So you're able to calculate with Courant number equal 1, you don't have any problem. You have consistency, you have everything. The calculation is beautiful. We've done thousands of these calculations over the last 40 years. 40 years? Yeah, 40 years. Yeah, since 1981. Okay, so Cosis was not doing it right. It's not criticism. I'm just telling the story as I see it, as I saw it also. Kosis wasn't doing it right. Who was Kosis? Kosis was a gentleman from, I think, from Greece that was teaching at Vanderbilt at the time. I don't know where he's right now. By the way, I told you the other day that I didn't know what happened to Duke, and I researched it afterwards on the web, hoping to find if he was dead. And in fact, he died in 2010. As far as Cunge, I don't know. I have not been able to confirm if Cunge is still alive or not. If he's still alive, he could be on the order of 95 years old. Cunge, okay? When Cunge dies, we're going to say a prayer, by the way, because we benefited so much with his work. Okay, so Kosis did this formula, and it's not quite correct, okay? Then Wyman and Lawrenson's, these people, I believe, were working out of Australia. I could be wrong on this, but Wyman and Lawrenson did a paper in Australia. They were also coming up with all kinds of situations. What was the problem? The problem was that if in the Muskingum you use the large reach, the problem will dump on you. It will become unstable. All kinds of weird situations. People didn't like that. Obviously, if a method misbehaves in practice, it's really bad method. You don't want it to misbehave in practice. It can misbehave in theory, but not in practice. Okay. You don't know what to say to your boss if the answer, instead of you expect 200 and it comes out minus 300. That's too bad, right? It could happen. Yes, it was happening. So people were not too confident on all of the entire Muskingum because of this problem. They call it the dip in the Muskingum. Another thing was that the Muskingum was limited to x between 0 and 0.5. 0.5 to achieve pure kinematicity. I believe I invented that word. The condition of being kinematic, kinematicity. I wrote that the first time in my book. And it was limited x equals 0 because people said that you could not go beyond 0. You cannot go less than 0. But in the Cunge method, when you put x equal less than 0, it works fine, beautifully. So then there was an issue there. What's going on here? And the answer was that as long as the moment matching is preserved, meaning if you want to preserve the moment matching between analytic and numerical, according to Cunge's definition, the x could be negative. So that had not been written very well at the time. So we wrote it here. So as you can see, now we have the same thing in here. Okay, the same thing. By the way, the C's and D's is an interesting story that I quite do not understand, because I put it in my book thinking that it was a great idea. I developed the Reynolds number, redefining it, not as the other gentleman had done. And it was something new concept, but I have to report to you that it has not caught on. And after 40 years, people are still talking about the x and the k. And to me, that's, excuse me, dumb. Because the x and the k have no meaning. The meaning is C and D. But at any rate, that's the story. And as far as I know, from my presentation or my publications, they're all in there. They're to be used if people want to use it. I can't force people to use stuff that they don't want to. Okay, so choice of space steps. Again, we have here, this stuff in here. Let me see who is I'm quoting in here. Miller and Cunge. Also, Miller and Cunge said something about this. Okay, historically, the parameter x has been interpreted as a weighting factor, and this led Miller and Cunge, among others, to suggest a lower bound for x. In other words, even Cunge said that x should be greater than 0. But I should tell you at this point that Miller and Cunge, who is Miller and Cunge? Miller was a professor somewhere in the East Coast, somewhere exactly I don't know where. And in 1975, Professor Yevevich called a symposium together with Professor Mahmoud, who was one of my mentors. And the symposium was an unsteady flow. And I attended the symposium. There's a 3-book publications on that symposium. And this publication of Miller and Cunge is from that symposium. And I'm given to understand, I'm guessing here, that Miller wrote the paper and put Cunge's name in there. And Cunge just signed off without reading it. Believe me, that does happen. People don't read what they publish, okay? And some people, of course. And they're busy. So I don't know if Cunge really knew what was in there, because Cunge's paper would give you the impression that you don't have to lower x to greater than 0. And yet the Miller and Cunge paper does say it, okay? Wyman and Lawrenson, which at the time were big Muskingum guys, said, since x may not realistically decrease below 0, there's a limit to the allowable degree of subdivision, which implies a lower limit on delta x. That's, of course, wrong. Also, we figured out, we have another method, very simple method, and we figured out when you set x equal to 0, the delta x has to be this value here. And it turned out we discovered that this was the basis of the Kalinin-Milyukov method. So I say that the Kalinin-Milyukov method was kind of similar to the Muskingum. You know, as a matter of fact, I have a method which could be considered a type of Kalinin-Milyukov, and we're going to talk about that later on. Okay, so I didn't research the Kalinin-Milyukov method. I just looked at it briefly and found out that there was a lot of commonalities between the method, the Kalinin-Milyukov method, and the method, the simplified Muskingum that we were looking at the time. Okay, so the choice of time steps, the time step has to be small. You cannot have a 24-hour flood and have a time step of 12 hours. That would be ridiculous. That would just lead to failure. If you have a 24-hour flood, the time step has to be 30 minutes or less. Typically, we use 30 minutes or 15 minutes. You have to resolve the variability in sufficient number of points. As a matter of fact, we happen to believe that the resolution of 100 is recommended. Because nowadays we have the computers. We cannot say, oh, I don't have a computer. No. So resolution, so divide the 24 hours in 100. So that gives you 15 minutes or 10 minutes or whatever. We used extensively 7.5 minutes because it gives you 8 divisions in the hour. Okay. Okay, so then the Qur'an numbers follows accuracy criteria. Okay, so what we decided to do at the time is to do a lot of tests. I've always believed in quantity. I'm going to do a lot of tests. And when I'm analyzing the test, I'm going to find out the rules. So then I proposed to do 144 tests, and we did that, varying everything. We varied discharge, we varied base flow, we varied everything. Okay? So, and also consistency, closely related to accuracy, is the subject of consistency. In the context of this study, accuracy refers to the avoidance of negative outflows. Sure, if you have negative outflows, you don't have any accuracy. Consistency refers to the ability of the routing method to produce the same results regardless of grid size. Okay, when we had our discussions with Fred Thur in the year 1980, when we met for the first time in San Diego, when I had just arrived to San Diego, and he said that they, of course, realized that the convex method was non-consistent. So they were trying to fix the consistency method, and they came up with the Atkin method, and he said that it was better, but not quite. He called it the first patch, meaning we're trying to fix this, but we don't really know what we're doing. And I said, Fred, I can promise you that the Muskingum-Cunge is going to be 100% consistent. And since he had wrestled with the consistency problem for several years, he figured that I was saying something that either could not be believed or I was a genius. It was not me, it was Cunge. So that's why he gave me the resources, the money. He says he wanted to see the consistency. And in fact, I proved to him that it was consistent. Okay, what is the consistency problem? For instance, if a certain hydrograph is obtained at the end of a given channel using 10 spaces, 10 space steps, a consistent method will produce the same hydrograph if instead of only 2 spaces have been used. In other words, the consistency gives you the right answer regardless of the discretization, regardless of the resolution of the grid. And that is done with Cunge's method, only with Cunge's method, because Cunge's is accounting for the diffusion, numerical and physical diffusion, while the kinematic wave does not account for physical diffusion. There is no physical diffusion involved in the kinematic wave numerical method. And that is why HMS is making an error, albeit small, when they calculate the so-called kinematic wave of HMS. It's an error because they're not calculating the diffusion, if any. Now, if the problem has no diffusion, then it's fine. But not all problems have no diffusion. It's a complex issue that sooner or later you will get to learn, but it is confusing. Okay, so we calculated, we figured out the numerical experiments, and at the time, I was going to use my great sinusoid, and Fred Thur says, oh, you know, Ponce, we've used this other method because we don't believe the flood waves out there are sinusoids. I said, oh, okay, fine. Sinusoid is simple, but if you want me, so what should I use? And he said, we use this gamma function, which I later subsequently put in my book, by the way, kind of make it complex. This gamma function number 21 does the job. So we were applying gamma functions, okay, and we, as you can see, we came up with channel 1, channel 2, channel 3, channel 4, channel 5, low flow, high flow, everything, all these numbers in here. We were running Fortran at the time. There was no Excel at the time. I mean, I don't want to spend a lot of time with this, but the first spreadsheet was called 123. The second one was Quattro Pro, and the third one was Excel. And then in the middle 90s, Excel took over. So it took them for 10 to 15 years to take over. Now the others died. Okay, so we plotted all the results for Curran and Reynolds number, and we found out that as long as you deviate from the center, all these are bad. Because I know we're looking at the hydrographs, right? But we were able to say that in this corner in here, not corner, in this middle between 0.5 and 1 and 0, and in between 0 and 0, this is where the good answers are. Reproducible, perfectly routed, and so forth. And so then we came up with criteria. But the fact of the matter is, the reason why it's here, it's because the Curran number is 1. The Curran number is 1, and that's it. Okay. And we have shown later, was it later? We have also shown, using the Cunge theory, that in fact, the Curran number 1 will drop the third order term, because Cunge didn't do that. He made a mistake in the algebra, and he said it, but he could not prove it. Well, we said it and we proved it. Okay, so the fact of the matter is, now we know after 20 years, 40 years, that if you fix the Curran number equal to 1, then you will get the right answer. Okay, now there's an interesting story in here. People have been working with this, and the Army Corps had also been working with this, because they were at the time doing their HMS and so forth. So I talked to them, and we were also generating overland flow models at the time. And the problem is that how do you fix the Curran number equal to 1? That's the problem. You got to if you're gonna have reproducibility. And the answer is, I discussed this with, I believe, with Danny Fred of all people, and also with Arlen Feldman and others. And the way to do it on the plane is you take the plane, you know the celerity, you know the delta t, which you prefix, and then from assuming c equal 1, you calculate the delta x. So the delta x is a calculated value, not a set value, but a calculated. Because if you set it, then you end up with the Quran not being equal to 1. And I do believe that HMS does that. And Danny Fred, when he was alive, because he already died, was also doing that kind of stuff. We were kind of sharing tricks. I figured this out and I did it on my own. Our calculator of overland flow is perfect. And then I gave it to one of our students to put on the web. And right now it's on the web. And it's also like perfect. It gives you constant. You change the delta t, change the delta x, and nothing happens with the calculator because the calculator does whatever it has to do. It's pre-programmed to do what it has to do in order to achieve Quran equal 1. So that's the story, the summary and the conclusions on this story. So I'm going to skip there or finish there. And I'm going to talk about the Muskingum-Cunge routing equations. I think we're progressing to finish on the 4th. That's fine. Listen to what I'm going to say because it's important for your homework. Okay? In the past, I didn't put this on the web, but people were really confused and I decided to put it on the web. Okay? So we start with this. Don't forget that this Thomas problem is a calculation per unit of width. So it's lowercase q equal 1.486 over n, Manning's n, d to the 5/3, s to the 1/2. That's the rating. It's called the rating, QD rating. When you talk about rating, you can talk about uppercase Q, uppercase A, and that's the rating. Or uppercase Q and lowercase y, that's a real rating, the natural, not the practical rating. But in theory, we're talking here theory, we're studying the problem. What we want to do in here, in no uncertain way, is to figure out what is causing the diffusion. Because it is a diffusion that we're trying to calculate in here. Is this way diffused? No. This way diffused? Yes. Why? Okay. So therefore, this is the rating of the kinematic wave. Okay, this is a rating. It's one rating. This is the kinematic wave rating. Okay, so we can simplify that to Q equal alpha d to the beta, where alpha is the coefficient and beta is the exponent of the d. Alpha is 1.46 over n or times s. That's good. That is in some sense similar to the conveyance, okay? Similar, but not quite. Beta is 5/3 for the rating, exponent of the rating, 5/3 unit width channel. D is therefore from here is Q over alpha to the 1 over beta. V is equal to Q over D, so it's this. You can plug in the numbers in there. C is equal to beta times V. So this is C over here. And then from there you calculate C, which is our routing parameter. Is a lowercase c, which you already know, because it's dq dA, times delta t over delta x, which you already know. We must have said it. In our problem, we said it. Delta t, I believe, is 6 hours and 3 hours, and delta x is 25 miles. Okay? And notice that we have to choose the 3 hours and the 25 miles carefully because this should be around 1. Because if it's not around 1, it's going to mess up. So the 3 hours and the 25 miles is set up. It's closely matched in order to make it work. Because otherwise, I'm not going to specify a problem for you that doesn't work. Okay? And then D is equal to this. We already know by definition. And N is just accuracy of the approximation, which ought to be greater than 15. And we do find that this, in fact, that this problem barely makes it as a diffusion wave. A little more than 15 is like 16 or 17. So it's cool. So those are the formulas that you have to use in your Excel spreadsheet. These are the formulas, okay? So with that then, I am now going to go to the 4th paper, which is the analytical verification of Muskingum routing. And there's a video on this, which we may have time, I don't know, we'll see. Analytical verification of Muskingum routing. Let me say that this is a great paper. It's a real great paper. Why am I saying that? Not because I wrote it, but it's the first time that you have a numerical calculation, which is supposed to be in error, and a theoretical calculation, which has no error. It's closed form, theoretical. And they give the same answer. They give exactly the same answer. from which we can conclude that the Muskingum-Cunge method is 100% theoretically based. There's no empiricism in here. It's all theory, okay? As Cunge said it quite correctly. So we decided we were going to do this in 1996 because through the 90s, 80s, through the 80s, there were people in the literature, there were non-believers of the Muskingum-Cunge. Can you believe that? That's true. There were non-believers, and they kept saying that that they used the word hocus pocus. This is hocus pocus, and you guys know what that means, because they did not understand the concept of numerical diffusion. Now, physical diffusion was developed and conceptualized by Hayami, and that's a hard concept, but it can be done. But from there to numerical diffusion, that is a very big step. I took it in the early 70s because we were in the lab, we were studying this. We found something and we realized this is really important, okay? But even through the 80s, and people were not, did not have that experience, and they were refusing to accept the Muskingum-Cunge. Like I said, through the 80s, they were coming up with papers, I don't want to mention names, in the literature where it said, hocus pocus hydrology. And so I said, I'm going to shut these guys up. I'm going to prove that I do a calculation, and the calculation is the same number. I said, can I do that? And yes, we did it. I engaged Lohani, who came from India, and Sheikhi, who was one of our top students in the year 1995, to help me out, to kind of support me. You know, I was obviously the leader, and they helped me out for about 4 or 5 months, and we did this paper. And in this paper, like I said, I'm going to point out to you exactly where it is so that you can see. All this jazz about the theory. Now, 500 miles. One is analytically computed values based on diffusion wave theory, meaning Hayami's theory as expressed by Ponce in our S paper. Number 2, numerically generated values using constant parameter Muskingum-Cunge model, because it had to be constant parameters, because we're comparing analytic with numeric. The analytic does not have any nonlinear, so you have to compare apples and apples here. Okay, so it has to be constant parameter. Now look at these numbers. 176.74 is the theory. 176.70 is the numerics. The error is like 1 in 10,000. No, 4 in 17,000. So there's 1 in 3,000. That is extremely small. In this business, if you could call it a business, it's nothing, okay? So we showed perfection here. The other numbers are similar, okay? They're all kind of reproduce what I said, that the method was correct. So the well-known Muskingum method has been known for many years. The Muskingum routing were theoretically derived by Cunge, based on the approximation error obtained by a Taylor series of the grid function. Although the parameters so derived have been shown to work reasonably well, the link to the analytical expressions and hydraulic diffusivity have yet to be demonstrated in actual routing. That's why people were saying, we don't believe this, okay? So we're going to compare. So we're going to look at the background. The Muskingum-Cunge, an improvement method, uses repetition here. Now, this is important here. This allows routing in the Muskingum-Cunge allows routing in ungauged streams with a reasonable expectation of accuracy, which would otherwise be possible only if the streams were gauged. In other words, for the Muskingum to use, you have to use gauge, and you don't have any gauges. In hydraulics, you do, but in hydrology, you don't. Why? Because hydraulics is focused on a channel, and if the channel is important, it has already been gauged. And if it's not important, you don't have any business doing a calculation. It's in one more channel of millions of channels. Okay, so there's gauges in hydraulics, but in hydrology, you got a watershed and you got to calculate parameters, and you have one gauge in the entire watershed, you know, or 2 at most. But how many channels are there? They have hundreds of channels. You cannot transpose the gauges, the cross-section change. You know, the cross-section determines the gauge and so forth. So it was, to do a hydrologic calculation without a gauge was hit and miss. And that's what was propagated by Lindsley in the 50s and 60s. They were saying, Well, we don't have the X, but if you want to run this thing, assume 2 or point 2 or point 3. They said it outright. Assume point 2 or point 3, that works most of the times because it's in the middle range. But it was not correct. It had nothing to do with the physics, okay? Because at that time, that's the best we could do. So we improved Ponce, and we improved this over here. We have the same equations, Courant number, cell Reynolds number, and the same CD equations, okay? Cunge formulation is based on diffusion wave theory, the applicability of which was confirmed by Ponce. We confirmed the applicability of the diffusion wave theory. Pioneering analytical work on diffusion wave theory is due to Hayami. We already know Mr. Hayami, who reasoned that the large-scale longitudinal mixing caused by channel irregularities could be effectively modeled as a diffusion process. Ponce and Simons used the theory of linear stability, which you already know. We started with this class. We started with this paper in this class, to derive celerity and attenuation functions for sinusoidal perturbations of the state uniform flow. In other words, we have the right answer theoretical. But see, the theory is good, but it cannot be used in practice. You can use to support, but not to actually get a number. Unless, of course, you did what I did in the lab here, which proved a specific case. Okay. In this paper, we use the findings of Ponce and Simons to calculate theoretical, I bolded it today, theoretical, that is analytical peak outflow and travel time for a series of sinusoidal hydrographs, and to compare these results with those obtained using the numerical method, because we have a numerical method. So again, the equations are the same. And here's the trick. The wave attenuation follows an exponential law. First, I didn't do this, and I wasn't getting anywhere. I said, this guy, I'm doing something wrong in here. And what I was doing is that you are talking about the average of the values. So this is the decay exponential function. That's why this formula had to be written in this way. Okay, and the amplitude propagation factor, that is from our paper, from our S-curve. This equation 11 came from our S-curve. Okay, in 12, already from S-curve also. We already know that. And this one right here, also from the S-curve. This also from the S-curve. And finally, when you combine 11, 12, when you combine 10, 11, and 12, and I ask you to do that, I'm not going to quiz you on it, but I did it this afternoon because I just wanted to make sure I was correct. We reproduce from 10, 11, and 12, we reproduce 13. That's a good assignment for you to do just to get going on this. It's not easy, but it can be done. Okay. Then the numerical testing, we use Thomas problem. The Thomas problem is a great problem for testing. We tested the applicability, it should be greater than 30, and it was equal to 31. This is summary and conclusions. I already told you, okay? And I already told you about that. And I plotted the hydrographs. They look beautiful, sinusoids, okay? They look beautiful sinusoids, and that's what we could do. So we acknowledge the support of the Indian gentleman who came with the United Nations Development Program. He helped on this paper. That's basically it. So success, total success in this regard. So what I'm going to do now, I got 5 minutes here. I'm going to finish with the paper, kind of reiterating what we had said, kind of to point out the salient features of this. By the way, if you're wondering about the music, it's my favorite music, Tchaikovsky's Piano Concerto. Let me say this. After we published this paper in the year 1996, there was no more mention of hocus pocus in regards to the Muskingum-Cunge in the literature. We totally obliterated the opposition. It is so obvious that, I mean, there was no other way to go. This is the formula I've asked you to verify its correctness on your own. Because that's the formula how we calculated the attenuation. The BI times T. There's a T in here. Diffusivity known, time base known, celerity known, totally known. I noticed Mr. Santos is not there. Is he there? Okay, we'll keep going. I should mention to you at this point that I know I looked at this figure and there's a bug in there, a typo. In the ordinance, it say Q parentheses, and I'm having that fixed in the next couple of days. I'll edit the video and fix that error. That's just a typo. In other words, your results are going to show this thing. They're supposed to show that the result of your Excel. This picture is of a flood in the Upper Paraguay. I was there in 1995, and it was lucky that when I was there, they had a huge flood, so I took pictures.
Professor?
So at this point, I have 2 minutes to go, and I'm going to use them. So what we're going to do in the next meeting, which is Wednesday, is to go to B5, which is the type of Kalinin-Milyukov method, much easier than Kalinin-Milyukov, I think it makes sense, this one. Then we're going to go to revise the variable parameter. We did this with Chaganti in I forgot the date. Look, there's an error in here. The date is 1994. Chaganti was also a student at San Diego State. I have a bug in there. Then we're going to talk about Thomas' problem in online computation, the program that Diaz, another student, helped us in the year 2016. And then Bupalapari that did the amplitude and phase portraits, that would be our introduction. Not our introduction, Cunge already talked about that, but we're going to reiterate what Cunge had said in a better way, much clearer way, because Cunge was not clear in what's presenting. And finally, hopefully we're going to end with a ferric paper that opened my eyes in regards to dispersion. Because we talked about diffusion, but not dispersion. Dispersion was the third order, and Ferric did it. And he's a good man. He is working out of, I believe, the Krell Lab. Ferris, 1984, he used to work for the Krell Lab. What is the Krell Lab? The Krell Lab is similar to the Davis Lab, but only that it's in New Hampshire. It's called Krell, C-R-E-E-E-L. It's Coal Regions Research and Engineering Lab of the Army Corps of Engineers. It's one of 3 wet labs, so-called wet labs, that the Army has. The third wet lab is at Vicksburg. So Vicksburg, Dartmouth, and Davis is where the Army has their 3 wet civil engineering labs. So with that, I am going to finish in here. Wish you a good day tomorrow. Wednesday, we'll see you Wednesday. For those of you that are taking environmental hydrology, we will see you tomorrow. Thank you very much. If you need to contact me, you know where to find me. Thank you. Bye-bye.